Hello everyone, this is Madhuri, working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology, Hyderabad. Today, I am going to discuss about DC motors as a part of DC machines course. So, coming to the first and foremost thing while discussing about the DC motors is its working principle. So, basically, we know that the motor is a device which converts the electrical input to a mechanical output. So, it is nothing but it converts the direct current to a mechanical work. So, how to produce this direct current in the motor and how does this current carrying conductors in the rotating part of the motor experiences a force and which is given as a mechanical output in the motor is seen under the working principle. So, it basically works on the principle of Lorentz law. Lorentz law states that a current carrying conductor, when placed in a magnetic field or in an electric field, it experiences a force. So this force is nothing but the Lorentz force, and the magnitude of this force is given by F is equals to BIL. F is nothing but the magnitude of force, B is nothing but the magnetic flux density, I is nothing but the current flowing in the conductors of the armature, and L is nothing but the effective length of the conductor. So this direction of force which is experienced by the conductors in the armature is given by the Fleming's left hand rule. So we can see in the picture here, when the three fingers, that is the thumb finger, the index finger and the middle finger, are held perpendicular to each other in the presence of a magnetic field in a DC machine or a DC motor, the thumb indicates the direction of force and the index finger indicates the direction of magnetic field or nothing but the magnetic flux density B, and the middle finger indicates the direction of current. So all these three terms and the direction of force is given by the Fleming's left hand rule, which is together called as the working principle of the motor. So basically, the working principle of a DC motor is nothing but it works on the principle of Lorentz law, which states that whenever the current carrying conductor is placed in the magnetic field, it experiences a force. So how does the conductors experience the force and how the resultant magnetic fields are set up in the armature conductors are seen in the next slide. So for simplicity, we are just considering a single conductor among the group of conductors which are there in the armature. So when this single conductor is placed in the presence of the magnetic field, you can see the north and south pole here, which are nothing but the magnetic poles which are situated in the stator of your DC machine or the DC motor. So this magnetic field, that is nothing but the north and south poles or the pole core in the stator of the DC machine, will produce the main flux or the main magnetic field. So you can see the flux lines which are passing from the north pole to the south pole, and the direction of flux lines denoted by these arrow marks. So this is nothing but this MNA is nothing but the magnetic nodal axis. This is the axis which will be perpendicular to the magnetic field set up by the stator poles. Coming to the figure B, in this figure B, we can see that a flux is also set up by the conductors at the ends of the conductors. So this flux is called as the flux set up by the armature. When there is an interaction of these two fluxes, that is the main flux and the armature flux, a resultant flux is formed. So which can be seen in the next slide. So if we consider, so by the interaction of the flux produced by the coil and the magnet, we can see that a resultant field is developed in the conductor. So this resultant field will make the conductor to rotate. So this is nothing but the force experienced by the conductors on the either end of the conductors. So this force is responsible for the rotation of armature in the motor. So this resultant field tends to move in the direction of this main MNA, axis of MNA, which is nothing but the magnetic nodal axis. So this field exerted by the conductor will make the coils in the armature rotate. So this is how the conductors in the armature grooves or the armature slots in a DC machine or a DC motor will start rotating. So let us consider, as I have told, the field FM is the main field which is set up by the magnetic poles, in which the direction of this magnetic flux which is set up by the main field will be in the clockwise direction. So when the current flows through the coil, they produce their own field, say Fr. So Fr is a magnetic field set up by the conductor. So this Fr tries to come in the direction of the main field. So these both fields, both Fm and Fr, will try to align in same direction. So when they align in the same direction, it produces a torque. So this torque is responsible for the driving or for the rotating of the armature in the DC motor. So this torque, this particular torque will become zero when this conductor is in perpendicular to the magnetic field. So when this conductor moves in the perpendicular direction to the magnetic field, the torque will be zero. When the torque will be zero, you may understand the force exerted on the conductors may be zero and it has to stop rotating. But that doesn't happen because we have number of conductors. Z is nothing but the number of conductors. We usually, denote the conductors with the help of Z. So there are number of conductors in the grooves or in the slots of armature. So if one among the conductors in the armature moves in the perpendicular direction, the next conductor will move parallel to the magnetic flux or the main field flux, so that the torque does not become zero, and which makes the continuous rotation of the armature. So whenever some conductors move in the perpendicular direction, there are the other conductors which align themselves parallelly to the magnetic field, with which the driving torque will always be responsible for rotating of your armature conductors. So now we are going to see what is back EMF. The next concept is nothing but the back EMF. We have already discussed about the EMF generated in the generator, in the DC generator concept in our previous classes. So taking the same relation, EB is equals to P into phi Z and P by 60A. We know that P is the number of poles of the DC motor, phi is the flux per pole in the DC motor, and Z is the number of conductors, armature conductors, N is the armature speed, which is usually given in RPM. A is number of the parallel paths in which the conductors of the armature are placed. So all these parameters are constant except the speed, because the speed varies according to the load. So keeping the remaining all quantities as constant, we can say that the back EMF or the EMF which is generated in the motor is directly proportional to the speed of the motor. So now we will analyze the three cases of this back EMF. What is the significance of back EMF in a motor? So whenever we give a DC supply, consider a voltage V is applied across the motor terminals. As it is a DC motor, we apply a DC voltage V across the motor terminals. Then the armature starts rotating and the torque is developed in it. So this is the basic working of the motor. So when the armature rotates, the armature conductors cut the magnetic field set up by the poles. So as per the electromagnetic induction, we know that the back EMF or the EMF is induced in that current carrying conductors in the armature. So this is nothing but called as back EMF or counter EMF in the motor. So which is given by EB is equals to P into phi Z and P by 60A. So taking the relation, EB is directly proportional to N. Before going to see the significance of back EMF, let us see, we know as per Lenz's law basically states that effect opposes cause. So induced EMF always opposes the cause of prediction for it. So induced EMF, if we take it as back EMF EB, so if the cause of prediction is nothing but the supply voltage V, so we see that this back EMF will always oppose the supply voltage. Here the cause of generation of back EMF is nothing but the rotation of armature, as we know that in the presence of magnetic field, if a conductor rotates, an EMF is induced with the help of Faraday's laws of electromagnetic induction. So this generation of back EMF is responsible for the rotation of armature. So this rotation of armature is due to the torque, and this torque is due to the armature current. we know that EB opposes V, and this EB is responsible. EB is produced by the rotation of armature. This rotation of armature is due to torque, and this torque is due to armature current. So armature current is again due to the supply voltage. So we can see that ultimately the prediction of EB is directly linked to the supply voltage. So therefore the back EMF is always directed opposite to the supply voltage. So moving on to the significance of back EMF. So this back EMF will make the DC motor work as a self-regulating machine. How does it work it as a self-regulated machine? Will be analyzed in 3 cases. So first case is nothing but the no load condition. So we know that this presence of back EMF will make the motor to drive or to draw more amount of armature current, or the armature current which is sufficient to develop the required torque to drive the load which is attached to the motor. So this back EMF is responsible for drawing of the armature current, which is again indirectly responsible for the prediction of torque. So we take the first case whenever the motor is running on no load. Whenever we see that there is no load being applied on the motor, we require a small torque. So as we give the supply voltage V, it drives a current I. The small amount of armature current is responsible for a small amount of starting torque. So this torque should be, this required torque which is used to rotate the armature conductor should be in such a way that it should overcome the frictional and windage losses during the initial stage of the starting of the motor. So this small torque which is required to overcome the frictional and windage losses and the no load condition during the no load condition. So we require a small amount of armature current because we require only small torque to rotate our motor. So that's why the back EMF will be now nearly equals to the apply voltage, because whenever there is a small current in the armature, there is a small drop occurring in the armature. When this value is small, the EB value, the supply voltage, will be very much nearly equals to the EB value. So as this drop is very small due to the small armature current, as we require the small amount of torque in the no load condition, so your supply voltage is very much equals to back EMF but with an opposite polarity. Second case, when we load the motor. What happens when we load the motor? First thing is, generally, as we analyze it generally, when we put a load on the machine or a motor, first the rotating part of the machine will slow down. So the first effect we see is it causes the motor to slow down. Therefore, whenever it slows down, the speed of the motor will fall down. So we have seen a relation between the EB and N. So when the speed decreases, we can see that the back EMF also reduces. Hence, the back EMF will also fall in this particular case. So this decreased back EMF will draw more amount of armature current. So when the armature current is more, according to the relation, we have the torque relation for motor as torque is directly proportional to the flux and the armature current. So whenever this armature current is high, we can see that the torque is also high. So in this particular case, we can see that as the speed decreases when you load the motor, your EB will also decrease. So this decrease in EB will draw more amount of IA, that is nothing but armature current. So which makes the torque also to increase, as we have a direct relation between torque and IA. So whenever IA increases, your torque will also increase. This increases the driving torque. So this increase in driving torque as a motor slows down the motor will slowly start to slow down, but it does not completely stop. So in this case, whenever the motor slowly slows down, the armature current is adjusted in such a way that it produces a required torque or a sufficient torque to drive the load. So this is what happens when you load the motor. First thing is nothing but your speed drops, with which, as there is a direct relation between EB and N. So as the speed drops, your back EMF will also drop. So when this back EMF drops, it draws more amount of armature current, which again increases the torque, which is given by the relation, according to the relation, torque relation. So which makes the motor to slow down slowly, but it does not completely stop. So as the motor gets slowed down, when the motor is slowing down, again the armature current is adjusted in such a way that it provides the required torque or a sufficient torque to drive the load. So this is the case when the motor is suddenly loaded. And the final case, when the loaded motor, when we remove some load which is actually applied on the motor. So what happens? We know that the driving torque is already in excess of requirement whenever the motor is loaded in the previous case. So in that case, whenever you decrease the load, the speed slowly pulls up, the speed increases, so with which your armature gets accelerated. That means the speed of the armature increases. So armature speed increases as we have direct relation between EB and N. So when speed increases, the EB also increases, which causes the armature current to decrease. So whenever EB increases, a small amount of current is enough to produce the required torque. So motor will stop accelerating when the armature current is just sufficient to produce the reduced torque required by the load. So when we remove the load, we require less amount of torque. For that, we require less amount of armature current. So that's why your motor stops accelerating when these two quantities are reduced. So it follows, therefore, the back EMF in the motor regulates the flow of armature current. So with which we can say that your motor, the significance of back EMF in the motor is nothing but EB makes the motor as a self-regulating machine. According to the application of load on the motor, so it makes the motor a self-regulating machine. This is the significance of back EMF in a DC motor. So that's all for today's session. So in today's session, I'm going to conclude it. So in the conclusion, we are going to discuss whatever the topics we have covered in this lecture. So first I have covered about the working principle of DC motor. So in working principle of DC motor, we basically discussed about the Lorentz force law. We have the Lorentz force law, which actually states about the force experienced by the armature conductors in the DC motor. Then we have the Fleming's left-hand rule. This Fleming's left-hand rule will give the direction of magnetic flux density, current, and as well as the force experienced by the conductors in the DC motor. Then we also have a basic principle, that is nothing but Faraday's laws of electromagnetic induction, for explaining about the dynamically induced EMF in the DC motor. So all these three laws were discussed under the working principle of DC motor. Then we have discussed about the back EMF. So back EMF, we have discussed that the back EMF will always oppose the supply voltage, and we have also discussed about the significance of back EMF in three different cases. In case 1, we have discussed under the no load condition. In case 2, we have discussed about the fully loaded condition. And in case 3, we have discussed a situation where the fully loaded condition, a partial load is removed from the fully loaded DC motor or partially loaded condition. So in these three cases, we have seen that overall how the back EMF varies with respect to the driving torque and how the required armature current is drawn into your motor to produce the required driving torque for the rotation of your armature. So this analysis of back EMF in these three significant cases will make the DC motor run as a self-regulating machine. So the types of motors and the other respective topics will be discussed in the next class. Thank you.